Alright guys, so this is Dr. Perkins, welcome to EKG. So we're going to be talking about rhythm description. So let's start off with the most difficult of all the rhythms, normal sinus rhythm. Now a lot of times this is taught as the easiest of all rhythms, but the way I kind of look at it is this is the most difficult. If you can get a thorough understanding of this rhythm, this will serve as the baseline for all the other rhythms, right? So it's going to be definitely the baseline for your sinus rhythms, but your atrial rhythms and so on are in large measure based off of normal sinus rhythm. So we'll start off with the P waves. So the P wave is the first wave you see. It's the atrial contracting, right? And so these P waves are going to be upright, uniform, lead 2. What does that mean? Well, it means the voltage is going to be positive, aka the upright. Uniform, they all look the same, right? If you're wearing a uniform, you look the same every single day. You're dressed exactly the same. And lead 2, all right? So we're not looking at AVR or AVL or AVF because you might be positive in lead 2, but you'll be negative in AVR, right? And so if I said, hey, look, the P waves were upright, well, what lead were they upright in? Oh, they were upright in AVL. And then let's say tomorrow somebody's looking at lead 2. Oh my goodness, well, the P waves are negative. Yeah, but they were upright yesterday, right? So it just creates utter confusion. So they had to say, hey, this is the lead that I'm looking at. There's 12 different leads they could talk about. They chose lead 2. All right. So your PR interval is 0.12 to 0.20 seconds, and that's from the start of the P wave to right before the QRS starts. All right, and that's going to be a constant. Okay, so your QRS is 0.06 to 0.10 seconds, right? So 0.10 seconds or less is narrow. The other thing is it's going to be monomorphic. All the QRSs are going to look the same. They're not going to be looking very different. Next thing we got is the rate. The heart rate is going to be 60 to 100 beats per minute, and it's going to be a regular rhythm. Now, this is actually one of the most important parts of this sheet right here, where we're talking about why is this not why is normal sinus rhythm? Why don't we call it sinus bradycardia? What's the difference here? Right? Sinus bradycardia is going to look a lot like normal sinus rhythm. The P wave is going to be upright, uniform, lead 2, PR interval 0.12 to 0.20 seconds, and constant. Your QRS is 0.06 to 0.10 seconds, narrow, monomorphic. And the rhythms are going to be regular. So what's the difference there? The only thing that's different is the rate. In normal sinus rhythm, the heart rate is 60 to 100 beats per minute, but in sinus bradycardia, the heart rate's less than 60. All right. Why? Because you have a slow heart condition, right? So if normal is 60 to 100 and you're beating less than that, then you got to be less than 60. Sinus tachycardia will look just like normal sinus rhythm, will look just like sinus bradycardia. Well, what's the difference? The rate. In sinus tachycardia, the heart rate's greater than 100 beats per minute. In normal sinus rhythm, once again, the heart rate is 60 to 100 beats per minute, right? That's why normal sinus rhythm is not the same thing as sinus tachycardia, that heart rate. All right, sinus dysrhythmia. Everything, all this stuff right here is going to be the exact same thing as sinus dysrhythmia, except for the rhythm. In normal sinus rhythm, it's regular, but in sinus dysrhythmia, it's going to be an irregular rate. And so that's the major difference there. So why do we have some of these things? Well, I'm going to go into some of this theoretical right here. So this is the heart's electrical system. And so you got the SA node, and it's going to send out the electricity to the Batchman bundles right here. So as the electricity moves this top part of the heart called the atria, it's going to generate the P wave. You notice this is in gray and this is in gray. Why? Because I'm matching up the structures with the wave. So as electricity goes from here and through all these structures, that's the waveform that it's generating. Now, once electricity gets to that AV node, it's going to take a long time to kind of get through this. And so I refer to this as kind of like the timer. This right here, this area in red, is actually called the PR segment, or as I like to call it, the timer. So, right, and you just see a flat line right here. And then that's going to generate a QRS. One quick thing before we move on, what we have you routinely measured in EKG class is the PR interval. The PR interval is from the start of the P wave to right before the QRS. Alright, anyways, the next thing that happens is once electricity gets here, it's going down this his Purkinje system, and it's going to generate the QRS. So all electricity's made it all the way to the ends of the ventricle. Alright, so right here, the muscle squeezing, holding that nice tight contraction. Nothing's really going on here other than just the heart keeping a nice tight contraction. When the heart gets the message, hey look, time to relax, that's when you generate your T wave. U wave, you don't routinely see that on an EKG, but they say it's because it's the Purkinje fibers resetting. But that's what's going on here. So let's dive into it a little bit deeper. So why is my P wave upright uniform in lead 2? Why isn't it negative in lead 2? So what's going on right here is this is going to be my lead 2. And so in lead 2, this is going to be my right arm. This is going to be my left leg down here. And the sides with the most L's decides which way is positive. So the word right arm, no letter L's. Left leg, there are 2 letter L's. And so as I go from the right arm to the left leg, I'm going to be positively 2. Well, if I'm here and I want to get all the way down here, but I cannot use a diagonal line, I can only use up and down, left and right. How to do that? Well, if I go straight down, that's going to get me a lot closer to that left leg. But as you can see, I'm still a long ways away from it, right? So what has to happen? Well, I have to go to my patient's left, right there. And so both going down and to the left are considered positive in lead 2. All right, well, Dr. Perkins, how is this helping me figure out why the P wave is positive in lead 2? Well, what happens? Here's my SA node. So when this thing fires, what's going to happen? My electricity is going to go to my left. And let me change the color here for clarity. You'll see why in just a second. So it's going to go towards my patient's left. And it's also going to go down, right? So I'm at the top of the right atria, but I have to go down to kind of get towards where the atria meets the ventricles. And so what's happening? Well, my heart's electricity is going down into the left. And so when people do what you want them to do, you consider that as a positive, a good thing, right? Well, the EKG machine, it wants the heart's electricity to go down into our patient's left. If the heart's electricity is going down into the patient's left, right, that's going to be considered positive. So a positive plus a positive is still a positive, right? If somebody gives you $5 and somebody else gives you $3, you're feeling really good, really positive because you're getting all this money. Same sort of idea here. So your P wave, that explains why it's going to be positive, right? Here's this line right here is called a baseline. This is big fat 0. So as you can see, I'm definitely above the big fat 0. So I'm going to be positive. All right. Now, why is this uniform? All right. So if I were to put a GPS tracker on your bumper, and you're to drive home from ECPI, you're going to take the same route every single day, right? More or less. And so, here's you leaving ECPI, here you're going home, right? Next day, here's you leaving ECPI, here you're going home. So pretty much the same route every single day. That's exactly what's happening in the heart because electricity is taking the same route to go from the SA node to the AV node, to go from the SA node to the edges of the atria. The P wave is going to look exactly the same, right? Now, if my P wave started over here, every time this thing fired, it would produce a P wave that looked different than this one. I'm just going to make up a shape just for the sake of argument. Let's say it's going to look something like this, right? So every time this thing fires, it's going to look like this, the exact same way it did the last time it fired, but it's not going to look the same as it did this way. So just because we're being consistent and we're firing here every single time, that's why my P waves are uniform, right? In the two. All right. So every time this fires, the P waves are going to look exactly the same they did last time. Okay. Next thing. So why is it taking 0.12 to 0.20 seconds? Because the electricity has to move through the entire atria to get to the SA node, and then we have our timer kick in, that PR segment. Um, you know, so this will come into play a little bit later. But because we're starting and stopping at the same place, we're taking the same route, we're doing the same thing the same way, right? It's not going to take any shorter or longer. At ECPI, when I leave here at like 10:30 at night, there's like no traffic. And so it takes me pretty much 34 minutes every single day to get home. Yeah, I get a little bit of variation. Maybe it takes me 35, maybe it takes me 33, but it's still pretty close to 34. Why? Because I'm starting and stopping at the same place, I'm taking the same route home, and there's no traffic. And so that's kind of what's going on there. So that's why that PR interval is going to be pretty much constant. All right, so the next thing we got is this QRS. Notice the shape here. Once again, remember how each time this thing fired, it produced this shape right here? Well, each time electricity uses the His-Purkinje system in lead 2, it's going to produce this shape, right? And so that's going to be the normal shape. Just a quick side note, but that will be important later, is let's say I generate a QRS, but I start over here, right? I'm just going to make up a shape. It might look like this, right? But every time this thing right here fires, it's going to produce the exact same shape that it did the last time. So because I'm starting here every single time, my QRS is going to look exactly the same as the last time I fired. All right. Now the thing that it said is narrow. Why is it narrow? Well, one of the things is the electricity is going down and over here, right? We're using like a superhighway to very quickly get the electricity to the heart. And so, while the electricity is going over here, it's also going over here at the same time. Notice this one's pretty wide. Why? Because if I start here, I can't quite use the superhighway, right? I gotta go over here, then I gotta go over here, right? And that's gonna take about twice as long as if I start here. Why? Because only thing it's taking me is for the electricity to go down the superhighway over here, right? Why? Because the same time I'm going down over here, I got the electricity moving down over here. And so it's going to be pretty quick. All right. And so, yeah, those are some of the fundamental ideas behind this. And then you'll see where this is going to come to play here in just a second. Okay, so now on to our second rhythm. So it's sinus dysrhythmia. So we're going to start at the bottom. So sinus dysrhythmia is going to look just like normal sinus rhythm, except the rhythm is irregular. So what's happening? Well, remember that SA node that was at the top of the right atria, and it sets the heart rate for the heart. It says beat, 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 beat. Well, one of the things is your heart is very important for controlling your blood pressure. If you're beat, 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 your blood pressure is going to be a lot higher than if you're beat, beat, beat. And so your brain is constantly controlling how fast your heart is beating. If your blood pressure is too high, we're going to slow our heart rate down. If it's too low, we're going to speed it up. And so one of the things that's happening is we're breathing in and out all the time, right? Well, what does this have to do with the heart rate? Well, when you breathe in, we suck air into our lungs. How do we do that? Well, we drop the pressure in our chest cavity. And so, because the pressure in our lungs is lower than the outside world, we're sucking air into our lungs. When we breathe out, we up the pressure in our chest cavity. And so, because the pressure is higher in our lungs than the outside world, the air is going to leave our lungs, right? Well, going to the blood, the same thing's kind of happening in there. When we're breathing in, just like we drop the air pressure, we're dropping our blood pressure. Well, we don't want low blood pressure. If the blood pressure is too low, we're not getting enough blood to our brain and our vital organs and so on. So what we're going to do, we're going to speed up the heart. And so your heart rate will go up when you're breathing in. When you breathe out, your blood pressure is going to bump up. Well, I don't want high blood pressure. I don't want to have a heart attack or stroke. And so I'm going to slow my heart rate down, to bring my blood pressure down. And so that's what's driving that sinus dysrhythmia. Now, because my SA node is what's creating the heartbeats, my P waves are going to be upright uniformly too. Why? Because my electricity is coming from the same place every single beat. My PR interval, I'm starting and stopping I'm taking the same route every single day. So my PR interval is going to be 0.12 to 0.20 seconds and constant. All right, I'm not affecting anything in the ventricles, so everything's going to be totally normal there. My QRS is going to be 0.06 to 0.10 seconds. That's the definition of narrow. It's going to be normal looking. It's going to be monomorphic. All my QRSs are looking exactly the same. The rate is going to be 60 to 100 beats per minute. Now the rhythm is going to be irregular. Why? Because I'm adjusting my heart rate to stop my blood pressure from going too high or too low. Okay, so next rhythm, what we got? All right, so Sinus Bradycardia is our next rhythm. So once again, I'll kind of do the trick I did before. We're going to start here at the bottom, right? So what makes Sinus Bradycardia different than normal sinus rhythm? The only thing is the heart rate. Sinus bradycardia, the heart rate's less than 60 beats per minute. Normal sinus rhythm is going to be 60 to 100 beats per minute. Why is this not sinus tachycardia? Because sinus bradycardia, the heart rate's less than 60. Sinus tachycardia, the heart rate's greater than 100 beats per minute. So, given all that, what are we going to see? Your P waves are going to be upright uniformly too. Your PR interval is 0.10 to 0.20 seconds. Your QRS is 0.06 to 0.10 seconds, narrow monomorphic. Your rate is less than 60 beats per minute, and your rhythm is going to be regular. So that's all there is to it. Okay, so the next rhythm that we got is Sinus Arrest. So Sinus Arrest, the heart's beating, everything's going right, ba-bump, 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 and then deet, right, the heart stops beating. Now, one of the big keys is this pause is going to be less than 6 seconds long, and it's not going to be an exact number of heartbeats long. All right, why is this? Well, here's a couple of reasons why. Once again, kind of look at this bottom, work our way up. There are a few rhythms that look a lot like this. And so, we got to keep these things in mind. This is going to look just like normal sinus rhythm, except for that pause. This is going to look like cardiac arrest. The difference between cardiac arrest and sinus arrest is how long that pause is. If that pause is less than 6 seconds, that is sinus arrest. If the pause is equal to or longer than 6 seconds, that's cardiac arrest. Now, there's one other rhythm that's going to look just like this, but it's kind of tricky. And that's going to be that sinus exit block. What's happening with sinus exit block is that SA node is firing. Ba-bump, 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 ba-bump. Regular as clockworks. But the electricity cannot get out of that SA node. In order for it to show up on the EKG, the electricity has to be moving. Once the electricity stops moving, it becomes invisible on the EKG. Because electricity is not moving in that sinus exit block, we don't see it. But once electricity is able to break out of the SA node, we get the heart just starts beating just like it never stopped, right? If I were to cover up the pause, you'd have no way of knowing that anything out of the ordinary happened. Why? Because the next heartbeat came exactly when you would have expected it to come had that pause not existed. What happens with sinus arrest, if I were to cover up that pause, you're like, wait a minute here. This pause is like 1.5 heartbeats long, or 1.9 heartbeats long, or 4.7, right? What the heck's going on here? Why is this heartbeat not coming when it should? But with Sinus X block, you're not seeing that. But everything else is going to look just like normal sinus rhythm, except for that pause, right? And so normal sinus rhythm, pause, back to normal sinus rhythm. And so when you're not in the sinus exit, when you're not in that sinus arrest, you're going to see P waves upright uniformly too. When you are in sinus arrest, you're just going to see a flat line during the pause. Once again, during the pause, you're seeing nothing but flat line. Outside of the pause, everything should be totally normal. PR interval 0.12 to 0.20 seconds, QRS 0.06 to 0.10 seconds, narrow monomorphic. Overall, your heart rate is going to be less than 60 to 100 beats per minute. Why? Because each second I pause is going to drag the heart rate down lower and lower and lower. We'll just start off with the 60 beats per minute. And so what you're going to do is if the pause was 1 second, well, then the heart rate's going to be less 50 or less. If the pause is greater than 2 seconds, it's going to be 40 or less, right? If the heart rate was 100 beats per minute, for each second long that pause is, you're dragging down that heart rate by about 16, almost 17 beats per minute. So it makes sense the overall heart rate is going to be a little bit slow, or than what you'd expect for normal sinus rhythm. Okay, so the rhythm. Yeah, if I'm starting and stopping, that's going to produce an irregular rhythm. So no surprise there. Okay, so sinus exit block. Going back down here to the bottom, what's going on? So it's just like normal sinus rhythm, but there's a pause. That's a whole number of heartbeats long. It's just like cardiac arrest, but the pause is less than 6 seconds. Once again, if the pause is 6 or more seconds, we call that cardiac arrest. The closest look-like is going to be that sinus pause. So what's going on with sinus X block? So what's happening is, the SA node is being ba-bump, 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 ba-bump. All right, and so what should be happening with each of those bumps is the rest of the heart, that the rest of the atria should be contracting. So it's just like, for example, you notice you're not hearing this anymore. Why? Because I put my hand in the way. And so that my hand's not able to hit the table like it should. But the second I pull my hand out of the table, you pick up exactly where you left off. And that's exactly kind of what's happening in that sinus exit block. The SA node is firing totally regular, but the electricity can't leave that SA node. It can't go to the atria. The second that blockage is no longer there for the atria pick up on the the very next heartbeat. Exactly when it would have been had that blockage ever existed. So other than that, totally normal. Without the pause, in the time before, the time after the pause, it's going to be normal sinus rhythm. During the pause, you're going to get a flat line. Obviously, the rate is going to be a little bit less than 60 to 100 beats per minute, and it's going to be regular because of those pauses. So that's what you got going on there. Okay, so sinus tachycardia. So let's start off from the bottom. So how is sinus tachycardia different than normal sinus rhythm? The rate. Remember, tachycardia is a fast heart condition. So my heart rate is greater than 100 beats per minute, right? And so that's the only thing that separates it from normal sinus rhythm in sinus bradycardia. Now, there are two other tachycardias that I'm going to kind of introduce you to. So a junctional tachycardia, the electricity is coming from the AV node. And so because the electricity is starting and stopping in opposite places, it's going to make inverted P waves. So in sinus tachycardia, the P waves are going to be upright and lead 2. But in junctional tachycardia, they're going to be inverted. All right. The other thing is because the timer starts when the electricity gets at the AV node. Depending on where we're at in the AV node, the QRS may happen before or during the P wave. And so our P waves can happen before, during, or after the QRS. You know, and so, but with the sinus tachycardia, the P wave is always going to happen before the QRS. Why? Because we start the timer for the QRS after we complete our P wave. The other thing is, if we have that P wave starts before the QRS in a junctional rhythm, because I'm starting the timer and the P wave at the same time, that PR interval is going to be shorter than normal. And so all those are going to be clues as to kind of what's going on here. All right, now with a ventricular rhythm, one of the things I tell the students, and I beat you guys up about this all the time, the atria, the top part of the heart, makes P waves. The ventricles, the bottom part of the heart, makes QRSs. So if my electricity is coming from the bottom part of the heart, I'm not going to have a P wave. I'm just going to have a QRS. So one of the things that's going to help us figure out whether this is sinus tachycardia or junctional or ventricular tachycardia is, do you have P waves? If you have P waves, it cannot be a ventricular tachycardia. The other thing you're looking at is that QRS. If the QRS is narrow, it is not a ventricular tachycardia, right? So sinus tachycardia is going to have a narrow QRS, but ventricular tachycardia will have a wide QRS. Otherwise, this is the exact same. So once again, this is going to look just like normal sinus rhythm, except the heart rate is going to be faster than 100 beats per minute. So P waves, upright, uniform, lead 2. PR is 0.12 to 0.20 seconds. QRS 0.06, 0.10 seconds. Narrow monomorphic. Heart rate greater than 100 beats per minute in the regular rhythm.